In episode 32, titled Eigenvalues and Eigenvectors, the intuition behind important directions, the goal is to understand eigenconcepts as directions that stay consistent under a transformation. Because DataX questions often describe dimensionality reduction and structure discovery in words rather than in equations. Eigen ideas can sound abstract, but at exam level, they are mainly about recognizing what it means for a transformation to have preferred directions and for some directions to matter more than others. When you understand that, principal component analysis, covariance structure, and even certain graph methods become easier to reason about because they share the same foundation. The exam does not require you to derive eigendecompositions, but it does expect you to interpret them correctly and avoid common misconceptions, like treating eigenvectors as raw features. This episode will define eigenvalues and eigenvalues in plain language, tie them to variance directions, and show why large eigenvalues signal dominant structure. You will also learn the small but important details that show up in multiple-choice distractors, such as sign flips and feature combinations. The aim is to make eigenintuition feel like a story about stretching and stability rather than a proof you must memorize. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at Cyber.Me in the Bare Metal Study Guide series. An eigenvector is best described as a special direction that, when you apply a linear transformation, stays the same direction, even though its length may change. In other words, the transformation does not rotate that direction into a different one, it only scales it, possibly reversing its orientation if the scale is negative. This is the heart of the idea. Most vectors change direction under a general transformation, but eigenvectors are the directions that remain aligned with themselves. If you picture a transformation as a machine that stretches, squeezes, and rotates space, an eigenvector is a direction that the machine stretches or squeezes without turning. The exam rewards this direction unchanged except scaling intuition because it is the simplest correct description, and it supports downstream reasoning in principal component analysis. You do not need to compute eigenvectors to use the concept. You need to recognize what they represent in geometric terms. When you can say eigenvectors are directions that survive the transformation without being turned, you have the core idea. An eigenvalue is the scale factor associated with an I-vector, meaning it tells you how much the transformation stretches or compresses that special direction. If the eigenvalue has magnitude greater than 1, the transformation expands that direction, and if it is between 0 and 1, the transformation compresses it. If it is negative, the direction is flipped as well as scaled, which is why sign can be tricky in intuition, though the magnitude still reflects dominance. At exam level, what matters most is that eigenvalues measure how strongly the transformation acts along a particular eigenvector direction. This creates a natural ranking. Directions associated with larger eigenvalues represent stronger transformation effects or stronger structure in the context where the matrix is describing data relationships. The exam may ask you to interpret large eigenvalues, and the right interpretation is usually about dominance, strength, or captured structure, not about raw feature importance. When you link eigenvalues to how much stretch happens along that direction, you can interpret their meaning correctly. Eigenvectors connect naturally to variance directions in principal component analysis reasoning, because principal components are directions that capture the most variance in the data. When you perform principal component analysis, you are looking for new axes, not the original feature axes, such that projecting the data onto those axes preserves as much variability as possible. Those new axes are eigenvector directions of a covariance-like matrix, which means they are special directions determined by the data's spread and relationships. The key is that principal components are directions in feature space that the data naturally stretches along, and eigenvectors are exactly how you represent those preferred directions mathematically. The exam often tests principal component analysis at the intuition level, asking what the first component represents, and the correct answer is usually that it is the direction of maximum variance. Eigenvector thinking makes that answer feel inevitable rather than memorized, because you understand that the covariance structure has dominant directions. When you can connect eigenvectors to directions of greatest spread, you are applying the idea correctly.
Large eigenvalues are typically interpreted as dominant structure or information because they correspond to directions where the data or the transformation has the strongest effect.
In a data context, a large eigenvalue associated with a covariance matrix implies that along that eigenvector direction, the data varies a lot, meaning there is a strong pattern or spread captured by that component. Smaller eigenvalues imply less variance along their directions, which can represent noise, minor structure, or redundant dimensions.
This is why dimensionality reduction often keeps the largest eigenvalues and their eigenvectors, because those capture the most meaningful structure while discarding small variance directions that often carry less signal.
The exam may describe compression, noise reduction, or focusing on the most informative dimensions, and large eigenvalues are the mathematical signal for which directions are informative.
This does not mean that small eigenvalues are always useless, but it does mean they contribute less to overall variance captured. DataX rewards this ranking intuition because it supports correct choices about keeping components and understanding what is lost when you compress.
Covariance matrices are a commonplace eigenvectors show up as principal components, which is why the exam often ties eigenconcepts to covariance reasoning. A covariance matrix summarizes how features vary together, and its eigenvectors represent orthogonal directions in feature space that align with the data's variance structure. The eigenvalues of that covariance matrix tell you how much variance lies along each eigenvector direction, which is why they are used to rank components. The exam may describe a process of taking a dataset, computing a covariance-like structure, and then extracting principal directions, and that description is essentially principal component analysis. You do not need to compute the covariance matrix by hand, but you should recognize that its eigenvectors define the principal component directions. This is also why transposition and multiplication show up in earlier episodes, because covariance calculations involve those operations and lead naturally into eigendecomposition. DataX rewards recognition of this pipeline because it turns a collection of terms into a coherent workflow. When you understand that covariance eigenvectors become principal components, you can answer many principal component analysis questions with confidence. A helpful way to practice eigenintuition is to use a rotation and stretching story because it makes direction unchanged tangible. Imagine a transformation that stretches space more in one direction than another, like pulling a rubber sheet longer along a diagonal line. Most arrows you draw on the sheet will change direction after the transformation because the stretching distorts angles. But the arrow aligned with the stretching direction stays aligned, it just gets longer. That arrow is an eigenvector, and the amount it stretches is the eigenvalue magnitude. If the transformation also flips that direction, the arrow points the opposite way, but it still lies along the same line, which is why sign can change without changing the underlying direction. This story helps you understand why eigenvectors represent stable directions and why eigenvalues quantify dominance. The exam rewards story-level intuition because it allows you to interpret what eigendecomposition is doing without derivation. When you can explain eigenbehavior as stretching and compressing along special directions, you are capturing the core meaning. A common confusion is treating eigenvectors as raw features, and the exam expects you to avoid that mistake because it leads to incorrect interpretations about what principal components represent. Eigenvectors in a feature space are typically combinations of the original features, meaning they define new axes that are mixtures of features rather than one-to-one mappings to single original columns. This is why principal components can be hard to interpret as feature importance unless you look at loadings, because each component draws from several features. The exam may offer distractors that describe eigenvectors as the most important original feature, which is incorrect because eigenvectors are directions, not single features. You should instead think of eigenvectors as weighted blends of features that define a new coordinate system aligned to the data structure. This is also why dimensionality reduction can create components that capture shared variation among correlated features. DataX rewards understanding this because it demonstrates you know what is being transformed and why interpretation requires care.
Another small but important detail is that sign flips do not change the meaning of eigenvectors in the context you will see on the exam, because an eigenvector and its negative represent the same direction line.
If you reverse a vector, it points in the opposite direction, but it still lies on the same axis, and principal component directions are axes rather than oriented arrows in a meaningful sense. This is why software outputs can show a principal component with the opposite sign compared to another run, without any real change in what the component represents. The exam may test this with a subtle statement about eigenvectors changing sign, and the correct response is that the direction is equivalent because the component axis is the same. This matters because learners sometimes interpret sign flips as changes in meaning, which is not correct in the common principal component analysis context. The meaningful information lies in the subspace and the variance captured, not in the arbitrary orientation. DataX rewards this because it shows you understand what is invariant and what is a representation artifact. Eigenthinking links to stability, compression, and noise reduction, because selecting dominant eigendirections is a way of focusing on strong structure and discarding weaker directions that often carry noise.
When you compress data by keeping only the top components, you are projecting onto the subspace that captures most variance, which can reduce noise and improve downstream modeling stability.
This is also why eigenideas show up in regularization and conditioning discussions, because eigenvalues can indicate whether a system is ill-conditioned, meaning certain directions are weakly defined and sensitive to noise.
In practical terms, very small eigenvalues can indicate near redundancy and can create instability in inversion-like operations, which ties back to earlier episodes on singularity and numerical stability.
The exam may not ask you to interpret condition numbers explicitly, but it can ask about redundancy and stability in a conceptual way.
Eigenintuition supports those answers by highlighting that some directions carry strong information and others are weak and noisy. DataX rewards this because it connects linear algebra concepts to practical modeling reliability. Eigenideas also appear in graph methods and spectral clustering, which you may see later as ways to find structure in networks and similarity graphs. In those contexts, eigenvectors of graph-related matrices can reveal community structure, partitions, or smooth variations across the graph, and eigenvalues can indicate how strong those structures are. The exam may mention clustering using graph representations or may describe finding groups in a network, and spectral methods are a family that relies on eigendecomposition intuition. You do not need to know the full derivation to answer exam questions about the idea, which is that eigenvectors can reveal important directions of structure in a system, whether that system is a dataset covariance or a graph connectivity matrix. This reinforces the theme that eigendirections represent stable structure under a transformation, and the transformation differs depending on the context. DataX rewards this broader linkage because it shows you can transfer a concept from principal component analysis to other structure discovery settings. When you see eigenvectors as structure-revealing directions, you can navigate these questions more calmly. The exam focus should remain on decision use, not on derivation proofs, because DataX is measuring applied understanding and correct interpretation under constraints. You should know what eigenvectors and eigenvalues represent, how they relate to variance capture, and why large eigenvalues signal dominant structure. You should also know what can be misinterpreted, such as equating eigenvectors with raw features or overreacting to sign flips. When you can keep your explanation at the level of, "This is why we choose these directions and what that accomplishes," you will answer exam questions in a way that matches the expected reasoning. This also keeps you from getting bogged down in algebraic details that are not being tested, which preserves time and clarity. DataX rewards learners who can stay in the right abstraction layer and still be precise. When you can say what the method does and why, you are meeting the exam's intent. A reliable anchor for this episode is that eigendirections persist and eigenvalues measure dominance, because it captures both definitions and their practical meaning. Eigenvectors represent directions that remain aligned under a transformation, which makes them stable reference axes. Eigenvalues represent how strongly the transformation acts along those directions, which allows you to rank structure by importance. This anchor also supports principal component analysis intuition, because principal components are the stable directions of variance structure, and eigenvalues quantify how much variance each captures. Under exam pressure, the anchor helps you remember which is which and prevents you from mixing the roles. It also helps you interpret important directions language, which is often code for eigendirections with large eigenvalues. DataX rewards this because it produces consistent, correct interpretations. To conclude Episode 32, explain principal component analysis direction choice using eigenintuition, because that is the most common exam application of these ideas. Start by stating that principal component analysis finds directions in feature space that capture the most variance, and that these directions are eigenvectors of a covariance matrix, or a related matrix representation of the data. Then state that eigenvalues indicate how much variance is captured along each eigenvector direction, so the first principal component corresponds to the largest eigenvalue and captures the dominant spread. Emphasize that these directions are combinations of original features, not single features. And a sign flip does not change the meaning because the axis is the same. Finally, tie it to purpose by explaining that selecting the top components compresses the data while preserving dominant structure, which supports noise reduction and stability. If you can narrate that reasoning clearly, you will handle DataX questions about eigenvalues, eigenvectors, and important directions with calm, correct judgment. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.